Hello again. So today, the topic of today is the Game of Life Kata, and I have opened the web page here on the left. You can see it on the left side here. So I don't want to explain the Game of Life. You can look it up in Wikipedia or basically it's similar like Minesweeper. You have generations of cells in a grid, and depending on how many neighbors this cell has, it will continue to live or it will die, or maybe it begins life, right? And we will do this today in Clojure and using Emacs editor with the Cider Clojure plugin, Cider IDE plugin. And I'm a very beginner of Clojure, so don't expect too much from me, and I will have to look up a few things from time to time. But nevertheless, I'd like to do this in Clojure and in a test-driven style. So we do test-driven development, right? So I have prepared a little project, and I just want to open the project, and I'll open it. Let me check the project file. Yes. So this is a simple project. We're using Clojure 1.9, and well, there's nothing fancy. I thought maybe at some later point I want to make a visualization of the Game of Life using Quill. Check out quill.info on the web if you want to know what it is. But yeah, so I have created a first test file. I want to start with the rules, and for the rules, for simplicity, I want to combine the tests and the production code just in this rules file, because yeah, it's easier to handle. Normally, certainly you have to have the production in a separate file in the sources folder. So what we need to do is to connect Cider check-in, to connect it to the REPL. Yep, let's close this. And actually, I don't want to have this in this format. Yeah, okay, let's put this away. Right. So we have, I hope you can see it, we have the rules down here. It says a living cell with less than 2 neighbors dies. So this is our first, basically this is our first test, right? So we can create a test, dev test, what do we test? We test the new state, a new state test, and the syntax for Clojure.test is that you have to have this is, and then you can compare something, and depending on whether the comparison is true or false, it'll bail out with an assertion error, or it goes through, right? So what do we want to test? So a living cell with less than 2 neighbors dies. So when it says a living cell, there seems to be some kind of state. So a cell has a state. It knows whether a cell can be living, or it can be, it's dead. And it has neighbors, so it has surrounding neighbors. and if the neighbors are less than 2, the cell will die in the next generation state. So we compare is equal. I want to test if it's equal to 0, meaning it has died, when we have one neighbor. So I would call this function new state 2, and the current state is living, right? Now let me compile this. No, there's a compiler error. Because it doesn't know the new state function. So we have to create the new state function, new state, and then I have the number of neighbors and I have the current state. And to make this test pass, I have to return a 0, right? And it compiles. Let's run the test, and the test passes. So this is our first passing test. Let's create a new test for the next rule. Is equal 1. It survives. So let's read it first. A living cell with 2 or 3 neighbors survives. So in order to survive, it has to live before, right? But and we expect it to live when we give it oh, wait a second. This here should have 1 neighbor, and here we use 2 neighbors, and the current state is 1 for living, right? So let's compile it and let's run the test, and there's 1 failure. Certainly there's 1 failure because we just returned 0 here. So now we have to put in some conditions on when to return what. And therefore we use the condition, and we have the actual condition is, so the condition keyword, you can have multiple conditions which are each checked, and the first one that is correct, it will be taken, right? So the first, in order to make the first test pass also, is if smaller neighbors than 2, I want to return 1. No, 0. And greater neighbors than 1, I want to return 1 for when there are 2 or more, 2 or 3 in this case, neighbors. So let's compile this and run the tests. Okay, so the tests all pass. Good. So let's continue with adding a new test case. So what's the next test case? I forgot my Pomodoro. So what's the next test case? A living cell with more than 3 neighbors dies. So what we could assert, so what we could also say is that no matter if the cell was living or it was dead, it will be dead if it has more than 3 neighbors. The same applies to when it has less than 2 neighbors. No matter if it lived or if it was dead, it will it will be dead if it has less than 2 neighbors, right? So let's say we want to have it dead, and when the cell has more than 3 neighbors, so let's give it 4 neighbors, and we make it live before. Let's compile, let's run the test, and there's one failure. So we now have to implement the condition. The condition is that when we have more than 3 neighbors, the cell will die, right? And there's still a failure. Where's the failure? Oh, wait a second. What happens here? So it will go into, yeah, so it will evaluate this one first, and this will return a 1. So we probably have to turn them around. Probably have to turn them around, and now they pass. Good. So let's go to the last rule. A dead cell with exactly 3 neighbors becomes alive. So is equals 1, new state, from 3 neighbors. When the cell was dead, we expect it to be alive. And this also passes, but we have to add a special case for when the cell yeah, I think we have to add a special case for when we have 2 neighbors and the cell is dead, because in this case the cell will not come alive. It will only come alive if there are 3 neighbors, right? So is equals 0 for a new state with 2 neighbors and the cell did not live before. And I believe this test should actually fail. There should be one failing test. Yes, so this test fails because it will go into this here, but but it should not, or at least the case when we have exactly, wait a second. So I think this is okay, but the case where we have exactly 3 neighbors, we have to make some differentiation there. So a cell with 3 neighbors, it will always be alive, right? So so a cell with 3 neighbors will always be alive, but a cell with 2 neighbors, equals neighbors 2 and equals state. The current state is zero. When the cell is dead, it will continue to stay dead, right? But when the cell is, where is it? When the cell is not dead, it will continue to live. So when it, yeah, so that's, I think that's the differentiation we have to do here. Let's see. Yes, they all pass. So far for the rules. Yes, I think there's no more. We could add more tests here, but a test for 0, but I don't think we have to, because we have pretty much covered all cases here, right? Let's continue with a grid. I want to have a grid. So those are the rules, and now I want to have a grid. The grid knows how the grid can do grid operations. So it can do operations on a two-dimensional vector, right? And the grid knows how many. The grid should know how many neighbors it has and what the current state of a cell is. Yes. So let's create a new file, a new buffer, and we call it grid test, and we save this file. Let's yank this in first. Grid test, and we save this file as grid test.clj. And yeah, let's start with test, dev test, get state test. So I want to know the state of a cell of a grid. Is equals dead for a function get state, which has a position of 1 and 1, and which is applied on a vector 0, 0, 0, 0, 0, 0. So this is a two-dimensional vector, and we have x or row and column position, and we expect this test to fail because yes, so even the compile, it doesn't compile even, because we have to add this get state function, and it'll take a row and a col position and a grid. And now it compiles, but the test fails because it returns nil. So we have to return something, and to make this test pass, I just return 0. Excuse me. Let's run the test and it passes. Okay, so let's add a new test. Is equals 1 when get state in position 1, 1 with a grid 0, 0, 0, 0, 0, no, 0, 1, 0. That's the position I want to assert. This should be A1. And it fails. So, so what we have to do now, we have to create a vector function or list function get in, it is called, and I think it operates on a grid, and we have to pass the row and the column, or x and y if you wish, and this returns yeah, and if we can also yeah, you see it here. If the key is not found, then we can return a default value, which is in this case should be 0. And the tests pass. Yes. So I think this will be fine. So let's create a new test to get, let's call this neighbor count. Neighbor count test. And what does this count? The neighbors. So we have an equal function, and I want to test 0, that a cell has 0 neighbors when I call neighbor count on position 1, 1 with a grid of 0, 0, 0, 0, 0, 0, 0, 0, 0. Oops, it doesn't compile, so we have to create this function. Neighbor count, it takes row and col and a grid, and it returns 0. And the test passes. Good. Now I want another test equals, let's give it 1 neighbor. I'm wondering if we can shorten this, if we can make some combinations where this has to work, right? So let's give it 1 neighbor. This is 1 neighbor to the cell 1, 1 here. And this test fails because we just returned 0. So what can we do? We can what we can do is we can get the cell by decrementing the row and decrementing the column. 0 for a default value, and that should actually be 1. Yes, and this test passes. So let's add another test. Let's copy this. I'm not a big copy and paste fan, but So now I want to have two neighbors, and this would be, no, this would be two neighbors. Yes. Oh, wait a second. I think we can make it. We can make it quicker. We don't need so many test cases. We do the following. This would be 1, 2, 3, 4, 5, 6, 7, 8. Right? This would be 8 neighbors. So this should return 8 neighbors. But it certainly does not. So let's run the test. And it fails. So we have to make pass. But in order to make it pass, actually, we have to implement the real thing. So what is the strategy? We could copy add all, we could add all neighbors, or we can add together, we could accumulate all neighbors that are living, and they are living if they are 1. And so we go around the cell and add those together. So this is the cell on the left top, decrement row, then we need decrement row and take the column. Then we need decrement row, but increment the column. Then we go in the middle row, where we say not decrement row, but just take the row, but decrement the column. Yes. Now we have to increment the row, because we don't need to view this cell here. We can't just go one column below, right? Because the cell itself is not a neighbor. And then we have to increment the row and increment the row and decrement the column, and then we have to increment the row and keep the column as is, and then we have to increment the row and increment the column. And those are all neighbors that we want to add together. And the tests pass. So what we could do is to add an additional test which has some 6, 5, so those should be 5 neighbors. CK for compile, CTN for running the tests. Okay, so this still passes, which is good, and I think we can We can keep that. And if you see here, those two functions, they will be used in the rules. So we pass the result of those functions into the rules, and the rules, the new state function of the rules namespace will return the new state of this addressed cell. Yeah, I think that's fine. So next I want to create again a new buffer, and I call it game test. So I have so we are at the outer level now, a game. I want to have a game, and this game now combines the grid and the rules. Let's yank this in, call this game, save it as game test.clj. And I'm wondering how I can wait a second, how can I make, no, I want to have a separate column. X1, no, X1 is only one screen, right? X2 is making a new row, and X3 is making a new column. Okay, great. So I want to have my test results shown in here. Where are my, is it messages? Test report, Cider test report. Yeah, I want to have the test report on the right side instead of the left side. Yeah, so now comes the game. We have to combine all those things we did until now. But so what I want to do is I want to go take those four examples here step by step and create tests for it, where we use our new functions we have created, and to see and to basically implement the game. So the game is that it increments a generation. So in order to determine the new state of each cell of this grid, I want to initiate a new generation of the grid, right? So let's call this next gen for next generation. And what we have is equals 0, and we compare grids, right? So I want to compare grids. I have an input grid, or let's do it like this. Let's define it here. Def source grid 1, and the source grid is I want this here as my source grid, right? And it has 0, question mark. I put question mark as 0 because we don't know what it is. Okay, so this was my Pomodoro. So I just want to continue with my 25-minute Pomodoro. So so there we have one living cell, and that's in the center, and 3 dead cells. And I want to compare this with a result, and I want to and the result should be, after this new generation, is that actually the only living cell in the center will be dead. So this is the result grid, and we just compare the source. No, we compare the result grid with so we put this into our rule new wait a second. No, not rule. We put this into a function called, our next generation function. So we put in there our source grid. Source grid 1. Let's see if the parentheses. I must say, I'm really impressed by Clojure. It might seem awkward with all those parentheses, but it's really good to edit code, because even in Emacs, so it's properly aligned, and it's really I find it really good. So I like it very much, to be honest. Okay, so let's compile this. This should compile. No, it does not compile, because the next generation function is not known. Next gen, and it'll take a grid and returns a result grid. And what do we expect here? We expect a result grid 1. So we just return so we just return the result grid, and the test passes. So I could just continue with adding a new test case for our second example, right? So let's copy all this and call this grid 2, and the source is, so we have to look at this one here now. We have 1 living cell, 2, 3 living cells, and the cell in the center should continue to live. Well, I don't care about that at the moment. I just want to, in my head, calculate the result cell, the expected result of the new generation. So, and there's one question mark. Actually, there are a couple of question marks here. No, there's only one question mark, because the question, where the question mark is, this cell here, it has, if you look at here, it has 3 neighbors that are living, right? So this cell effectively will come alive. This cell here has 2 neighbors, so it will not come it will stay alive because it is alive. It's this one here. Then this one here has only 1 neighbor. It will stay dead. This one here has 2 neighbors. It will stay alive. This one here has 2 neighbors. It will stay alive. Yep, so. Yes, so let's go to the bottom row. This cell here has only 1 neighbor. It will stay dead. This cell here has 2 neighbors. It will stay dead because it is dead. And this cell here has also 2 neighbors, but it will stay dead. Okay, so let's run the test. there's a test failure here. Yes. So so in order actually to get through all our use cases here, I want to use the condition and compare the grids. So I want to compare the input grid with a source grid 1, and if this is 0, I want to return the result grid 1. And now let's do the same for the grid 2. Grid 2. Yeah, I just take the use cases and implement them as is. Okay, so there's a problem now. Equals 0, compare the source grid. When the grid and the source grid 1 are 0, then return I think I have to do this here. Yes, I think I have to do this in order to make this work. Yep, and it works. So let's move on with our third use case. So let's copy this. Grid 3. And now we have to look at this one here. So we have a lot of question marks in the source grid, but those two live, and at the bottom row, those 3, they live as well. So now, how is the result grid? On this one here, this one has exactly 1 neighbor if we look at the source grid, so it will stay dead. This one here has 2 neighbors, but it will stay dead. This one here has also 2 neighbors, but it will stay dead. This one here has 3 neighbors, so it will come alive. This one here has 1, 2, 3, 4 neighbors, so it will die. I keep the 0. This one here has 1, 2, 3 neighbors, so it lives and it will continue to live. This one here has 1, 2 neighbors, it lives, so it will continue to live. This one here is 1, 2, 3, 4 neighbors, it lives, so it will die. I keep the 0 here. This one here has 1, 2, 3 neighbors, it lives, so it will continue to live. Let's see the test fail first. Yes, and it fails. And now I have to add my case here. The reason I'm doing this is you will see this shortly. And it passes. Okay, so let's continue with our 4th use case. No, not this one. Okay, so now we have to look at this use case here. we have one living cell here, we have one living cell here, and we have one living cell there. So let's go through them and calculate how the result grid should look like. So this one here has no neighbors, it will stay dead. This one here has 2 neighbors, it will stay dead. This one here has 1 neighbor. 1 neighbor, it will die. This one here has 0 neighbors, it stays dead. This one here has 3 neighbors, will come alive. This one here has 2 neighbors, it will continue to live. This one here has 3 neighbors, stays dead. This one here has 2 neighbors, stays dead. This one here has 1 neighbor, stays dead. Yep. Compile, run tests, test fails. We need to add our test case, our implementation. For compile, run tests, they pass. So now we have test cases for all 3 use cases here, which should give quite a solid test background, I would say. Now we have hard-coded the results, and depending on the source grid, we return the right result grid. But we have all tests pass. So what we can do now, we can delete all this and implement our real algorithm, and then we can compare if all 4 test cases still pass. And if they still pass, we're pretty much done. If they don't, well, as long as they don't pass, we have a problem in our algorithm, right? So so let's implement the production code for the next generation. So what do we have to do? Basically, we have to go through each cell in our grid and calculate a new state of the cell depending on its neighbors and on its current state. So what we can do is we have two nested for loops. For sec expression and what is the for loop? It loops over the size of now we first loop over the rows, and then for each row we loop over the columns. So so really I have to look up how this works, how this for loop works. Concat conditional Clojure vector of so what am I looking for? Loop over vector Clojure, looping over vectors. Yeah, so I think no, I don't want the Stack Overflow, I want to have the for. Yeah, because yeah, I think I have looked at this and this is pretty much what we need here. So we have the row, and we can take the range of count the grid. Count grid will count the rows, And then we have another for loop which counts the column, which loops over the columns. Range, actually it's the same range, but count grid, so maybe we can make this a let, a local variable, because the rows and the columns should have the same size, right? But effectively we could also do this count row should be the same. Anyway, and now we have to produce our new result for each cell in here. And what is that? So we have to call our next again function and provide it with parameters for... No, we are in next generation, right? So what we have to do here is we have to call our rule new state function and give it parameters for the neighbors. Grid neighbor count, and this neighbor count takes the row, the column, and the grid, as far as I can remember. And the new state function also takes grid, get state, the row, and the col, and the grid. Yes. Okay, let's see what we're getting here. I think, yeah. So we have to include the namespaces. Use gov.grid test as grid, and use gov.rule test as rule. So that should work. No, what's the problem? Should this be a required or what? Should this be a required or? No. Rule test init, rule tests not found on class path. Okay, so what might be the problem here? I think it could be, I had this problem before, that I have to open up the grid and compile it again. And the same I have to do for the rules. I have to compile it again, so that we have so that the Clojure compiler can create class files, right? So, but there's something still. I'm wondering. Yeah, that's where my Clojure knowledge comes to. So rule is not found. Rule test as rule. Rule test is not found. File not found. I called it rules. Okay. I called it rules, not rule. Let's call it rules. And this here, yeah, I think I'll keep it as rule. And now it compiles. Okay, great. So we can actually run the test now. And all 4 tests fail. Can be cast as class cast exception. What can it be cast at? Persistent vector. Okay, so I think it might be because we're expecting a vector that we have to create a vector of our result here. Let's see. No. Count not supported. Count not supported on type long. Okay. So row. Yeah, row is not a row. Row is the index, right? So this certainly won't work. Let's see now, and now it passes. Okay. So yeah, I think that's pretty much it. And I think this is so we have implemented now all the rules, and we have implemented those 4 use cases, and I think those use cases are good enough to have a solid next generation calculation here, or a solid test backup, right? And so we could make a refactoring here to create a LED which has the count of the grid, so that we don't have to call the count twice here. But that's pretty much the only refactoring I could think of here. So maybe the Clojure geeks, they have a better, maybe there's something, maybe this double for loop can be done easier or better, or something. But otherwise, yeah, I think that's pretty good. So I must say I like the Cider Emacs IDE, and it's really lightweight. And once you have the key shortcuts, once you know the key shortcuts, it's really good. It really feels okay. So I like developing with Cider. There's also IntelliJ has this Clojure plugin. What's its name? I can't remember the name. I have tried it too, and it's also very good. And I usually use IntelliJ for Scala development or Java development or stuff like that. But for Cider, for Clojure, I really like the combination of Emacs and Cider. So, and as a next step, I'm thinking about doing this is to put a visualization on top of this. And I don't know. Okay, so my Pomodoro is over again. So we have used a little bit more than 2 Pomodoros, which is okay. So I don't know if you know quill.info. So this is a 2D, 3D library for Clojure, which is based on processing. You can have, if you're on some other JRE language, you can have a look at processing. But Quill has put in a nice Clojure-like API, and so this would be interesting to put a Quill visualization on top of our Game of Life implementation we just did. So maybe I do this in the next episode. Thank you very much for watching. Goodbye.